A very good morning, student. In the last video, we learned about Ka and the Kb values. What is Ka? The K is the acid dissociation constant at equilibrium, weak acid dissociation constant. Like the same, we learned about the Kb. Kb is the acid dissociation constant of the base. Now we are bringing a new term in relation to the Ka, that is called pKa. Generally we know pH is equal to minus log base 10 to the concentration of the H plus ion. Is it not? Means potential of hydrogen that we had learned in the last few classes. Now we are bringing a relation between the pKa and the pKb to prove that the pKa plus pKb is equal to 14. Last time we brought this value, but we didn't prove. We just introduced. Before we go to proving that concept, we want to know what is pKa. Whenever you have the pH, what is the definition once again? Negative log to the base 10 to the concentration of the H plus ion. Similarly here, pKa, whenever it comes, it is equal to negative log to the base 10 into the Ka value, means acid dissociation constant, dissociation of the weak acid. Once again, pKa is equal to negative logarithm to the base 10 to the Ka value. Generally, when Ka is very large value, we said it is a strong acid. But now, what we are saying pKa, we are saying pKa, it is the negative logarithm to the base 10 of dissociation constant of the weak acid. So whenever the K used to be very strong, acid used to be very strong. But now the pKa, whenever it is low, the acid will be very strong. Acid will be very strong. We are given the following equation: pKa is equal to minus log base 10 to the Ka. Similarly, we can write for pKb. What we can write for pKb? It is a negative logarithm to the base 10 of Kb. pKb is a negative logarithm to the base 10 of dissociation constant of the weak base, that is Kb. So pKb is equal to negative log base 10 to the K. Now what is the importance or significance of this pKa or pKb? The pKa or pKb will give you the strength of the acid or the base. For example, pKa is very small value. Now don't forget, Ka when it is very large value, larger the value, we said acid is very strong. Or now it is minus logarithm, means it is inversely proportional, we can say pKa whenever the value is very small, the acid will be very strong. So that's what we brought the significance of pKa and the pKb. Relative strength of the acid. pKa is giving the relative strength of the acid. Lower the pKa value, stronger will be the acid. For example, three acids are there: HCl, HB and HCl. HB, that is values 3, 4 and 5 and so on. So smaller the value, stronger the acid. Means HCl is more stronger acid than HB, which is more stronger than HC. In this method, we can decide the strength of the acid. Then what about pKb? The same method we need to apply. It expresses the relative strength of the base, and smaller the value, more is the strength of the base. So relative strength of the acid is explained by pK value. Smaller the value, very strong base will be XOH, YOH and ZOH are there. So 3, 4 and 5. Among this one 3, which is very small, the strength of the base will be more than the remaining. Now we need to prove that pKa plus pKb is equal to 10 to the power of, is equal to 14. But what we know, the value of pKa, generally we know one equation. In the previous class we had learned Ka into Kb is equal to 10 to the power of minus 14. Is it not? Ka into Kb is 10 to the power of minus 14. We need to take negative logarithm on both sides. Means minus log Ka into Kb is equal to minus log 10 to the power of minus 14. So that's what equation we have taken: minus log base 10. I am not expressing here. Anyhow, these are all base 10 forms only. K into Kb is equal to log base 10 to the power. We can show 10 or no problem. 10 to the power of minus 14. We know log A into B is equal to log A plus log B. So this is the form of log A into B. We are writing log A plus log B. So log minus of log Ka minus of log Ka plus minus of log Kb is equal to, this 14 is coming to the front part. We know the minus and minus are getting cancelled. Log base 10 is equal to 1. So it will be equal to only 14 only. So here minus log Ka. What is the value of Pk? It is equal to minus log base 10 to the power of to the Ka. What is Kb? Kb is equal to minus log base 10 into Kb. So in the place of this minus log Ka and minus log Kb, we are substituting Pka as the Pk, which are equal to 14. So we are able to conclude that the pKa and pKb is equal to the ionic product pKbW. This is how we are going to bring the derivation in a conclusion form. Here is continue concept like, for example, we generally know hydrochloric acid or hydrobromic acid or any of the acid we can take in general, like I am giving you a refer HCl on dissociation will give H plus and Cl minus. Means that acid was able to produce one H plus ion. It is called as its basic strength or basicity. In simple word we call as the basicity. The number of H plus ions that are generated by one molecule of acid is called as its basicity. So here how many H plus ions are generated, and only one H plus ion is generated. So it is called as a monobasic acid. What is called as the monobasic acid. Similarly, for example, if there is another acid called H2SO4, how many number of H plus ions will be generated here? 2 number of H plus ions will be generated. It is called as the dibasic acid. What is called as the dibasic acid. HCl is called as the monobasic acid, whereas the acid that is able to generate 2 H plus ions we call it as the dibasic acid, monobasic acid and the dibasic acid. But what if an acid is able to produce more number of H plus ions? An acid is able to produce more than 2 number of H plus ions, and the type of acid is called as the polybasic acid. What do we call it as the polybasic acid? Means the number of H plus ions when there are more than 2 per molecule which are generated on hydrolysis is called as the polybasic acid or the polybasic acid in simple terms. Further we got some definitions. What is called as the dibasic acid? An acid containing 2 ions, 2 ionizable protons is called as the dibasic acid. An example we got H2SO4 on dissociation that will give 2 H plus ions and SO4 2 minus ions. Generally we think these 2 H plus ions will be given in a single step. No. How do you eat chapati? In a single roll, will you swallow? You will not swallow in a single roll. But what you will do, you will just bite it into pieces and you will eat it. Similarly, whenever this acid is getting dissolved in water, it will undergo a step-by-step process. For example, this dibasic acid is there. First of all, one H plus will be given out, and in the next step, another H plus will be given out. For that, we brought from general equation H2X, some acid is there. On first ionization means one H plus is given. It is giving one H plus and H plus is given, remaining H minus is formed. Now this Hx minus is there, right? What we got the first step. On further dissociation there will be one more H plus, and this X already is having minus charge here, it is showing 2 minus charge. So this process of dissociation of acid does not take place in a single step. In case of dibasic acid, it is taken in a 2-step process. For each step, dissociation constant, which one acid dissociation constant must be calculated. For the first acid dissociation constant, we give concentration of the products upon concentration of the reactants. What are the concentrations of the products we have? Concentration of the H plus ions upon concentration of the Hx minus ion upon H2 or X. In the starting we got H2X. Now Hx, the second acid dissociation constant. Concentration of the products H plus H2 minus upon Hx minus. In this method we can able to do the acid dissociation constant for any of the acid by considering that the protons are not given up in a single step. In order to understand, we brought this basic and the polybasic. Already an example I had given for polybasic acid, and I brought the definition here. An acid containing more than one ionizable proton per molecule. More than two ionizable protons per molecule. It is called as the polybasic acid. So in this we are able to calculate the first acid dissociation constant, second acid dissociation constant, or we can take even the third acid dissociation constant also. Coming for the strength of the acid. The strength of the acid, it is depending upon two main factors. One of the factors is called bond strength. For example, H and A are the two atoms. It depends upon the strength of the bond. Second thing, polarity of the bond. So what are the two factors that are depending on which the strength of the acid depends upon? The strength of the acid depends upon polarity of the bond and the bond strength. Generally, in the case of these acids that are going to dissolve in water, we call the degree of hydrolysis. What do you call? Degree of hydrolysis. This means H plus ions after being formation, they will be surrounded by some water molecules. It's called hydrolyzed. What we say is getting hydrolyzed. How you will give this H plus ions when that is dissolved in water? You will say it is surrounded by H2O molecules to give hydronium ion. Means hydrolysis means what? Addition of water. It is getting electrons from the lone pairs of oxygen from the water molecule. So we will say it is undergoing hydrolysis. So the degree of hydrolysis does not depend upon the concentration of the solution. It is not depending upon the concentration of the solution. For such kind to be expressed, we brought one equation where the pH depends upon the pK values. pH depends upon the pK values. So the pH in which does not depend upon the concentration of the solution, very important, pH is equal to 7 plus half of pKa minus pKb. So how do you calculate the pH where the concentration does not depends upon the degree of hydrolysis does not depend on concentration? You say pH is equal to 7 plus half of pKa minus pKb. We will see one numerical problem on this, and next we will go for next concept in this chapter. Let us continue here, children, about the numerical that we have learned on the formula. pH is equal to 7 plus half of pKa minus pKb. One question is given. The pKa of acetic acid and pKb of ammonium hydroxide are 4.76 and 4.75. Calculate the pH of ammonium acetate. First you must know the equation generally to understand. What is the formula of acetic acid? Acetic acid formula says H3COOH. Generally it is a weak acid. pKb of ammonium hydroxide. Ammonium hydroxide is a weak base, NH4OH. When these both are combined, from the weak acid H plus will be given, from the weak base OH minus will be given. They are forming a water molecule, and the remaining salt is the acetic ammonium acetate, or the salt we call as the ammonium acetate. What are the asking directly to calculate the pH of the solution? So pH is equal to 7 plus half of 4.76 minus 4.75. So we can say 7 plus half of 0.01 or 7 plus half of 0.01 is equal to 7.00. 7 half of 0.01. How much are we getting, children? 7.05. Shall we say, or 0.5? You can say this half as 0.5 into 0.01. It will be around 0.05. Half is your thickness. Imagine half is equal to 0.5. This method. So you are getting 7.005 or 7.005. So that's what the pH of the solution. But now we are having some a little concept extra. This general textbook itself we call as up to there our concept is completed. Now we are entering into another small concept, very small concept. You see, generally, if you leave curd, it will become sour after 2 days. Yes or no? But it is traveling from the manufacturing company to our home. It is taking at least 2 to 3 days, but still it is not getting sour in. May you know what is the reason? Yeah, right. Or if you take the orange juice, you leave them from morning to evening in the atmospheric air. Morning you take the squeeze the orange juice, evening what you will observe, it will become too sour, you cannot taste it. But we have the pulpy orange from the manufacturers. How? It is not getting into acidic nature. How it is not getting into more acidic nature? Because into that they will add some salts. They will add some salts. They prevent the acid not to undergo ionization. The salts that they add, they will prevent them not to undergo ionization. So if an acid is not undergoing ionization, it will not become more acidic. That the simple concept brought under the title called buffer solutions. Buffer solutions. What is a buffer solution? Then let us see here. I am having some acetic acid. And for this acetic acid, I am adding a combination of its salt. What is the salt of acetic acid? We know generally it is ammonia acid. That's another secondary. We have the sodium acetate. What is the salt? Sodium acetate. So from acetic acid, we add sodium acetate. These acetate ions from both, they will not get this acid to undergo ionization. Means number of acetate ions, by increasing, they will combine with the H plus ions that are generated, and they will prevent the acetic acid not to undergo ionization. So a buffer is about the prevents to bring the change in the pH. It is a weak acid and it is a salt of the weak acid. And we know one of the weak base, ammonium hydroxide. What is the salt of ammonium hydroxide? Ammonium chloride. This ammonium chloride is resisting the ionization of NH4OH. Or in shortcut, for example, this ammonium hydroxide is there. It is dissociating. On dissociating, what will be formed? NH4 plus N, OH minus ions. But what you are adding a compound called NH4OH. Already NH4Cl you are adding. What you are adding? NH4Cl. Cl will not combine with OH. Is it not? It is combining. It is not combining. Now more number of H plus ions are there. NH4 plus ions are there. What did we learn under Le-Chatelier's principle? When concentration of a species on one side increases, the equilibrium shifts to the opposite direction. So when these number of ions are increasing, they will be combining with this hydroxide ions. And they will come back to form the NH4OH. Similar case in this one. So what is this substance we call? We call this substance as a buffer solution. See here, a solution which resists the pH change. The solution resists the pH change with addition of small amount of acid or alkaline is called as a buffer solution. A solution which resists the change in the pH with addition of small amount of acid or alkaline is called as a buffer solution. How are these buffer solutions prepared? These are prepared with the knowledge of pKa and the pKb values. If you want to see the ratio of these, it will be different. We are not having the ratio now. The pKa, whenever you take it, is nothing but the acid dissociation into the base 10 of acid dissociation count of the weak acid. So the salt and acid, this is the salt of it, the acetic acid, and this is the acid. Then both combinations is giving the acidic buffer. It is giving the acidic buffer. Whereas the salt and the base, their combination is giving the basic buffer. So based on the substance of that is added to the solution, whether acid is added, it will give an acidic buffer, and base is added, it will give a basic buffer. So what is the purpose of these buffers? They will resist the change of the solution. So by this we can understand buffers are the substrates that basically changing of the solution. How many types are there? Discrete buffer and basic buffer. Only one last topic is there. We will conclude our chapter equilibrium in the next video. That's called solubility product constraint. Thank you children. Have a nice day.